In this lesson, we'll try to consider a system of parallel forces acting in a plane and try to find their resultant. To begin with, let us consider a simple situation shown here. We have an object of arbitrary shape on which two forces F1 bar and F2 bar, which are parallel, they are acting and they are separated by a distance L as shown over here. Since they are parallel, F1 bar and F2 are parallel, we cannot use the parallelogram law to find the resultant, because parallelogram law requires that the forces meet at a point, which is not the case here. So we won't apply parallelogram law directly here, but we'll do something slightly different as shown here. Let us consider that we add two fictitious forces. Okay, these are the two forces we are adding. Magnitude of one force is S as shown here, and the magnitude of the other force is also S. So these two forces S and S, they form a set of forces which are equal in magnitude, opposite in direction, and they are collinear forces. And so this S and S, the force S and this force S, they are in equilibrium. And principle of superposition guarantees that by adding a system of forces in equilibrium does not change the state of the system in any way. So the resultant of F1 bar and F2 bar is the same as resultant of four forces, that is S, F1 bar, F2 bar and S. So here we have a slightly simplified situation in the sense that this S and F1 bar, they are meeting at a point. So we can apply the parallelogram law. We can complete the parallelogram here and say that the resultant of the forces F1 and S is as shown here. Let us call it R1. Okay, so the resultant of forces, similarly the resultant of forces F2 bar and S bar can also be found by applying parallelogram law here. Complete the parallelogram and draw the major diagonal. Call it resultant R2. So we can say that resultant of forces F1 and F2 is the same as resultant of forces R1 and R2, because all we have done is we added two forces S and S which are already in equilibrium. Now if you look at it, you have the forces R1 and R2 which are not parallel to each other. So we can extend their lines of action as shown here so that they meet at a point. So we extended this R1 back, this extended this R2 back, and they are meeting at a point. Okay, we can use principle of transmissibility to say that the resultant of this R1 and R2 shown here is the same as the resultant of R1 and R2 acting here, because principle of transmissibility guarantees that the action of a force does not change even if you move the point of application to anywhere on the line of action of the force. So we have forces R1 bar and R2 bar, and still we can say that the resultant of this forces F1 bar and F2 bar is the same as the resultant of forces R1 bar and R2 bar. Okay, now we can split this R1 bar into two components. One is F1, the other is S. Let me write that down. This is F1 F1 bar, and this is S. Similarly, this R2 bar, we can split it into two components. Okay, F2 bar and S. Okay, so we can still say that the resultant of this F1 bar and F2 bar is the same as the resultant of the forces F1 bar here, F2 bar here, S and S of the four forces put together. Now we can say that this S and S, they constitute a system of forces in equilibrium, and hence we can get rid of them. Okay, and we can get rid of those two forces. So the resultant of the forces F1 bar and F2 bar now is the resultant of these two forces F1 bar and F2 bar here. This F1 bar and F2 bar, they are along the same line. So we can in fact say that this resultant R, total resultant R, is the sum of F1 bar plus F2 bar. Simply add their magnitudes algebraically. Further, we can show that if we extend this line and it meets this in a point P, okay, and let us further assume that this is point A, this is point B, we can further prove that this AP by BP is equivalent to magnitude of F2 by magnitude of F1. That is, the this point P gives the location where the resultant of F1 plus F2 is acting. Okay, we know the magnitude of the resultant, which is algebraic sum of the magnitudes of the forces, and then the direction, which is parallel to that of F1 and F2, and point of application P, which is given by F2 by F1 is AP by BP. Okay, for a second let us assume that this is L1, that is AP is L1 and BP is L2. So we have L2 by L1 is equal to sorry, I think I wrote it slightly incorrect. L1 by L2 is equal to F2 by F1. So we can write L2 is equal to F1 by F2 into L1. Okay. Further, we can see that this L1 plus L2 is the distance between the forces. So we can write L1 plus L2 is F1 by F2 L1. This is equal to L. So you have L1 is equal to F2 by F1 plus F2, the total distance between the forces L. We'll try to use this result to find the location of forces in a general situation. If we assume your y-axis to be here, as shown here, and your x-axis in this direction, okay, assume that the distance between the point of application of F1 and y is x1. Similarly, the distance between point of application of force F2 and y-axis is x2. We can see that the location of the resultant as given by this coordinate x is, we can write x as you can see x is x1 plus L1. And we know this is x1 plus f2 by f1 plus f2 into L. We can now see this distance L is x2 minus x1. This we can simplify as f1x1 plus f2x1 plus f2x2 minus f2x1. So this and this, they get cancelled, and you have f1 plus f2. This is an important result, and we'll try to build on it in subsequent classes.